Before we get to 3.2, I've got couple things to mention between the sections. So I say after 3.1, but before 3.2, as we continue to develop more rules or shortcuts for taking derivatives. There's a couple things to say that are gonna concepts that are gonna come up in the midst of future sections as we move forward. So one big one is higher derivatives. So we want to give this some special attention. What are higher derivatives? Well, we know about taking what we might now refer to as the first derivative or the derivative, but it turns out you can take the derivative of derivatives. So I want to start with an example, and you're going to see some notation up here. I'll speak to that afterwards. So a polynomial is a good place to start. Let's say we have f of x equal to x to the fourth plus 2x to the third minus x squared minus 5x plus 1. Okay, so we can take the derivative, right? We know the rules for polynomials and powers from 3.1. So f prime would be 4x to the third plus 6x squared minus 2x. This derivative would be minus 5, and of course the plus 1 would go to 0. So we started with a polynomial, and then our derivative is a polynomial. The degree of that polynomial dropped by 1. But hey, what's preventing us from taking a derivative of this? Let's do it again. When we take a second derivative, we put a double prime. So that's f double prime, and that's literally the way you read it, f double prime of x. And well, in this case, same power rule, 12x squared plus happens to be 12x minus 2, and the minus 5 goes to 0. Hey, why stop here? How about the third derivative? And it's kind of hard to see there on the screen, but that's f triple prime, 3 little prime marks. F triple prime of x, in this case, would be 24x plus 12 minus 0. Let's do one more. If we take a fourth derivative, and there's a reason I'm going to stop at 4, we change the notation. In the next one, we're no longer going to write the primes, because I think people agreed at one point 4 primes is too much. It starts to get blurry, and it's hard to tell how many there are. So we do this instead, and let me sharpen my pencil and try and make that a little bit more clear. So what we've got there is a little 4 for the fourth derivative, and it's inside parentheses. So it's f and the little set of parentheses 4 of x, and you would just read that as the fourth derivative. Now you might wonder why we put the parentheses. Why not just put the number 4? Because if we just put the number 4, that could be confused with an exponent, like f raised to the fourth. So we'll put the little parentheses, and then now everybody knows, okay, we mean the fourth derivative of x. And in this case, well, that's just 24, and so on. So, oh, I do have a fifth. Okay, apparently I wrote a fifth. The fifth derivative, so that's a little 5 inside. That would be 0, and well, any derivative past this point, the sixth derivative, seventh, those would all be 0 here. Okay. Oh, I do have a sixth. Oh, okay. Well, I really went for it. Um, wow. Okay, we get it. Even at the fourth, I think we understand. Okay, so over here, just talking about notation if you're doing higher derivatives. So we've been using this notation, f prime, f double prime, f triple prime. And finally, we don't say prime anymore, we just say the fourth derivative of x, like that. You might use the y notation, y prime, y double prime, that's a little bit blurry, y triple prime, and the fourth derivative of y, like so. If you're using a Leibniz notation, then it'll look like this. Maybe you're using the dy over dx. Dy over dx, well, that's the first derivative. The second derivative, maybe that's difficult to see. Let me zoom in just on the notation. That's better. That's better. Dy over dx, that's a 2 and a 2. So d2y over d2, or some people do read this as squared. d squared y over dx squared. I will give you the reason for that in a moment, why that is the notation. But we keep that same pattern for a third derivative. We put a 3. It's like it's on the d, but in the denominator it's on the x, which is a bit weird. We don't put it on the y, but we do put it on the x. And then here, if you're actually writing the function in the middle, well, d over dx. Oh, looks like I have a mistake there. My bad. There should not have been a y. It should just be d squared dx squared. And then, of course, what you're filling in is right there. Okay, if you're curious, why is this the notation? Why do we put the square on the d and the x but not the y? Here's the reason. It's sort of a play on fraction notation, and that's why this notation became very popular. So I said it before, these are not fractions, but it turns out there is a connection, and we're kind of yet to see that. But just check this out. So d over dx, dy over dx. So think, okay, hey, we're trying to take a second derivative. So that's the derivative of the first derivative, right? Well, if we think of this as dy over dx, then if we take d over dx of dy over dx, these aren't fractions. This is not multiplication. Clearly, right? You're taking a derivative. But if you thought of them as fractions, and if you thought of them as at multiplication, then wouldn't it be d times d and dx times dx? And so that's where that notation comes from. They're not fractions. We're definitely not multiplying, but it sort of fits that style. Okay. You might be wondering, what's the point of higher derivatives? What's the point of a second derivative or a third derivative? I mean, a first derivative, describes the slopes of the tangent lines graphically, or instantaneous rate of change, instantaneous velocity. So what would be taking another derivative mean graphically, and what would it mean like for velocity? Okay, let me explain. We actually won't go into the graphing part. That will come later, and it will be actually something we spend a lot of time on. What like the second derivative, what that would mean for the graphs, really. We spend a lot, but we can make sense of like things like velocity. Okay, so what is this? A lot of times when you see the position of an object, it's described as the function s of t. You would think they would use p of t for position, but they don't. They use s of t. I'm not really sure why they do that. T is in time, like seconds, in a lot of cases. Okay, so what would it mean if we took the derivative of the position? So that's the instantaneous rate of change of a position. In other words, it's how fast you're moving. How fast are you changing position? And of course, we know this already. It's velocity. Okay, so the position of an object, then there's the velocity of the object is the derivative. And usually people will just refer to this as v of t, although that would be the same thing as s prime of t. Okay. Now imagine you're taking the derivative again, the derivative of the derivative. So think of velocity, okay, like speed. What's the instantaneous rate of change of your velocity? So think your velocity is changing. What do we call that? And in calculus courses, in my experience, when I put that out there, a handful of people know the change in your velocity is known as acceleration. Okay, so your acceleration is your second derivative of s double prime t. That would be the derivative of velocity, v prime t, but a lot of times we just call it by this, a of t. And we know that's the original, then the derivative, and the second derivative. I'm going to go one more. I'm going to go third derivative here. What's the instantaneous rate of change of your acceleration? Okay, so what's interesting, and this is kind of a physics thing, velocity, right? If you're just cruising along in your car, we don't feel velocity, right? If you're going 50 miles an hour, if you've got really, a nice car like good suspension, you might think you're just sitting still. You might not know you're actually moving. Like on an airplane, maybe you're going hundreds of miles an hour, but it feels like you're sitting still. Okay, acceleration though, then you start to feel something in your body, right? You can feel your body pushing back into the chair, as you accelerate, or if you hit the brakes and you decelerate, you feel yourself getting thrown forward. So then what would it mean to change your acceleration? Okay, so imagine, right, you're feeling yourself getting pushed back into the chair, but then they hit the brakes, they change the acceleration, you get thrown forward, and then they stomp on the gas again and you get thrown back into your chair, right? So that would be a change in acceleration. We call that, and it's kind of funny that it goes by this. It's called the jerk. That is the technical physics word, okay, for changing your acceleration, and it's like you're literally being jerked back and forth if your acceleration's changing. So that's S triple prime, kind of hard to see. Okay, S triple prime equals V double prime equals A prime, or it's just known as J of T for the jerk. We're not going to use the jerk in this course, but we will see acceleration. We'll definitely see velocity. Um, and so good to know, in case you see this in physics as well, that these things exist and that even higher derivatives do exist. Okay, there's one other thing I have to mention before we get on to the next section. So, of course, we've been talking about the tangent line, and the vast majority of the things we do, it's all about the tangent line. But we want to mention, because it comes up very seldomly, very rarely, the normal line. Okay, so the normal line, I don't know why it has that name. I don't know what's normal about it, but here it is. The normal line at a f of a, at some point on a curve, is perpendicular to the tangent line. Okay, so I got this curve here, and we imagine that point, right? That's maybe at A right here. We might as well put that, there's A. And we can draw that tangent line. We've been doing this a ton, right? Well, the line perpendicular to that is the normal line at the same point. Okay, so they cross at 90 degrees. You think, well, okay, I mean, tangent line tells you velocity, like the slope of the tangent line. What is the normal line? Why, what's useful about the normal line? So it turns out, again, Calc 1, we really don't hardly do anything with the normal line, but be aware, it will come up a couple of times in homework and things. The normal line is a much bigger concept when you take Calc 3, just for the types of problems and applications you do. But I can give you an idea. So imagine this is a road. Maybe you're looking down from a bird's eye view, and this is a road. Okay, and there's a car that drives along the road. So the car is just driving along. We're looking at it. We're looking straight down on the car. You think, oh, the tangent line, that makes sense. So the car, as it's coming around this corner, if they let go of the steering wheel right there, then the car is just going to go straight from that point on, right? So they're curving, they're in the middle of the turn, and then they let go of the steering wheel, or maybe they lose traction with the road, and they're going to just slide off according to the tangent line, right? Yeah, that's exactly it. So, okay, what's the normal line doing? The normal line is what the driver would experience, like the force he would experience. So as you're coming around this corner, if you're going very fast, you might feel yourself being pushed to the right side of the car, if you're driving this way. And so this is like how much force is being applied to the driver and is pushing the driver, away from the inside of the turn. It's pushing him toward the outside. It's also the amount of force that's on the tires. The tires have to grip the road so they don't slip out this direction. Okay. Another application would be, maybe something even simpler. I'll just draw it down here. I don't have it on my page. If you have a circle, and imagine, maybe this is like a toy a kid would have. So you're holding a string, and that string goes out, and you've got like maybe a little toy airplane, or something right there. Okay, that little toy airplane. That's a terrible drawing, but that little toy airplane, just kind of whizzes around, and they just kind of like spinning it in their fingertips here, and it's just flying around. So of course the tangent line, if the kid lets go of the string, that plane is going to fly out according to the tangent line, right? That's the direction it's going to move. So if you want to throw the airplane forward, then you release it out here at 90 degrees, and it'll fly that way. The normal line, which would be doing this, would again be that force that the plane is experiencing. So it's being pulled out this direction. The string has to pull it back in by that same amount of force to keep it, not to fly out and moving in that direction. So, okay. Normal line, that'll come up occasionally. Really the much bigger issue was those higher derivatives. Okay, we're going to start 3.2 next.